All right, thanks for the introduction. So after two very exciting talks from the quantum world, we're going to come back to the classical world now for this talk. So today I'll tell you about joint work with my fantastic co-authors, Joe Barth and Justin Shu, on a probabilistic separation logic. And so this is a new separation logic for reasoning about probabilistic programs, where we give a new interpretation to separation as probabilistic independence. All right, so first let's start off with some motivation for our work. Why should we care about randomized algorithms? Well, one good reason might be that they have many practical applications today, including in machine learning, differential privacy, and cryptography, which is our main focus. Okay, but why should we care about verifying them? And if you're willing to entertain the idea that these applications are important and that bugs can have serious consequences, then it's important that we get them right. Unfortunately, it's not so easy to check that we got them right using traditional software engineering techniques. And this is because in the probabilistic setting, correctness properties describe probability distributions over program runs rather than single traces. All right, fair enough. Why should we care about verifying probabilistic independence specifically? Well, it turns out that independence is a useful and often necessary intermediate assertion in proofs about randomized algorithms. And independence also simplifies probabilistic reasoning in the following sense. If we know that two random variables are probabilistically independent, in other words, they're uncorrelated, then reasoning can focus on one variable at a time without losing any useful information. And the benefit of this, of course, is modularity in reasoning. All right, so here's a simple example of where independence might come in handy. So suppose we have two parties, Alice and Bob, and Alice wants to send Bob a message over an untrusted network. Well, for security, they might want to use encryption, so both parties share a key K. Then on Alice's end, she's going to encrypt the key K, encrypt the message M under the key K, producing a ciphertext C. She's going to send that across the network, and then on Bob's end, he can recover the message by decrypting with key K. All right, and so what we should expect from a perfectly secret encryption scheme is that even if the eavesdropper sees the ciphertext C, he should learn no information about the corresponding plaintext M. And we can show that a scheme enjoys such a property in a few ways. One way is by a uniformity argument. And so the goal here is to say that the distribution on ciphertexts is uniform over some fixed set, no matter what the secret message is. And this implies a notion known as probabilistic non-interference. Another approach would be by an independence argument. And the goal here is to say that the distribution on ciphertexts is independent of any arbitrary distribution on messages. Put otherwise, this means that the distributions have no correlations between them, and so information about ciphertexts doesn't give you any information about plaintext. Now, of course, to show perfect secrecy formally, we could work in terms of these definitions, would say what it means for a random variable to be uniform, or what it means for two random variables to be independent. But now we need to analyze a lot of numeric probabilities, and this in turn can make verification very painful. Okay, and so the big idea of our paper is we designed a probabilistic separation logic for reasoning about basic properties such as uniformity and independence at a high level. So fortunately, using PSL, there's no need to analyze numeric probabilities. The proof system will take care of that for you. Okay, so here are the main contributions of our work and the roadmap for today. So our first main contribution is the design of probabilistic separation logic, or PSL. And this was heavily inspired by the very influential works on heap separation logic by Reynolds, Ishtiaq O'Hearn, and many others. And so first I'll start out by giving a quick refresher of heap separation logic. Then I'll tell you how we take some of those ideas and transport them to the probabilistic setting, giving rise to a new meaning of separation as probabilistic independence. Then, as our second contribution, we use PSL to verify the security of various cryptographic schemes. And so I won't have time to talk about all of them, but I'll give an example of how to use PSL to verify perfect secrecy of the one-time pad encryption scheme. And then, with what time I have left, I'll give you an example of how we use PSL to verify some fancier crypto called oblivious RAM or ORAM. All right, so let's first do a quick crash course on heap separation logic. So what do programs look like in heap separation logic? So here we consider a standard imperative language, also known as the while language, with constructs for manipulating pointers. And so these are shown in orange. What is the language of assertions in heap separation logic? Well, these are based on the heap model of the logic of bunch duplications, which is work due to O'Hearn, Pym, and Yang. And in this model, there are two components. And so the first component is a store, sigma, from variables to values. And this is also called the environment. And the second component is a heap memory mu, from memory addresses to values. And so the satisfaction judgment in heap separation logic looks like this, which we can read as the BI assertion phi holds for a given store sigma and heap mu. All right, so what's the star of heap separation logic? Well, that's separating conjunction. And so this formula can be read as phi star psi, or phi and separately psi. And this is sort of like your standard conjunction, but with a twist. And the twist is that it incorporates this notion of separation. And so what does this formula mean? It means that the heap can be split into two disjoint parts, satisfying phi and psi respectively. Okay. And now how do you reason about programs using heap separation logic? Well, there are program proof rules for manipulating Hoare triples. And in particular, there's a special frame rule that exploits separation to give you modular reasoning on the heap. And so what does this frame rule say? It says that if you can prove this triple with precondition phi, command C, and postcondition psi, then this disjoint part of the heap described by eta remains unmodified. And so you can preserve the formula eta through the command C. And this is sound as long as this side condition holds, which says that the free variables of eta don't coincide with the modified variables in the command C. All right, so that was heap separation logic. Now let's look at probabilistic separation logic. So what do programs look like in probabilistic separation logic? Well, here we consider a probabilistic imperative language, similar to p-while, with a construct for random sampling, shown in orange. And so this arrow with the $ over it denotes random sampling. And we also support randomized control flow, shown in purple. And so this enables you to branch on a random variable. What is the language of assertions in probabilistic separation logic? Well, here they're based on our new probabilistic model of bunch duplications. And so we too have two components. The first component is a deterministic memory sigma. So this is essentially the same as the store from the heap setting. And the second component is a distribution over randomized memories mu. Okay, so what's a randomized memory? Well, it's essentially the same as a deterministic memory, except the variables are ones that we've designated to be random. And so just to give you some, so here's the satisfaction judgment in PSL, which should look familiar. And we can read this as the probabilistic BI assertion phi holds for a given deterministic memory sigma and distribution over randomized memories mu. And now just to give some intuition about probabilistic BI, here's a simple example. So here we're going to toss two random coins and store them in x and y. Then we're going to store in z the logical OR of x and y. Okay? And so these tables shown here describe the random memories that occur with non-zero probability, also known as the support of the distribution mu. And each of these outcomes occurs with probability 1/4. All right, so what are some probabilistic BI assertions we can use to describe this distribution mu? Well, one formula would be the following, which roughly says that the variables x, y, and z are in the domain mu. If we wanted to be a little bit more specific, we could also use this formula, which says that x and y are uniform over the booleans in mu. We could also say something about the variable z. So here the tilde denotes probabilistic equality. And so this formula says that z and x or y are equal with probability 1 in mu. Okay? And of course, all of these formulas are fine to describe mu, but we might want to say something stronger about x and y, namely that they're independent. After all, they're the results of independent coin flips, right? And so this leads us to the star of probabilistic separation logic. And so we too have a separating conjunction, but we give it a new meaning as follows. So phi star psi holds over some distribution over randomized memories mu if we can factor it as the product of two distributions, mu1 and mu2, such that mu1 satisfies phi and mu2 satisfies psi. So to put this otherwise, this means that mu1 and mu2 are probabilistically independent. Okay? So if we go back to our previous example, let's say we wanted to describe mu using a formula saying that x is independent of y. In that case, what we need to do is be able to factor mu into two component distributions, mu1 and mu2, satisfying each of the conjoints. And so indeed, we can do that like so. So here in mu1, x follows the coin flip distribution as desired. And in mu2, y follows the coin flip distribution as desired. All right, so how do you reason about programs using PSL? Well, we have program proof rules for manipulating the familiar Hoare triples. And the nice thing about our rules is that they let you do probabilistic reasoning without having to analyze probabilities directly. We also provide a version of the frame rule that lets you reason modularly about independent random variables. So let's see some of these proof rules. So here's the random assignment rule in PSL. So in the premise, we require that x is not in the free variables of the precondition phi or the expression e. And in the conclusion, this says that if we start in an input distribution satisfying phi, and we assign e to x, then in the output distribution, x and e are probabilistically equivalent. And here's the rule for random sampling. So again, in the precondition, we have this free variable restriction. And in the conclusion, this says that if we start in an input distribution satisfying phi, then we uniformly sample from the set S and assign that value to x. Then in the output distribution, x is, of course, uniform over the set S. And being a fresh random sample, it's independent from the rest of the program state. All right, now here's our version of the frame rule. It looks a little bit more complicated than it actually is. And so shown in orange right now is the frame rule that we know and love from heap separation logic, except with this new interpretation of separating conjunction as independence. And shown in black are some additional but simple side conditions that I won't get into. And so what does this say? It says that if we can prove this triple in the top left, then the independent part of the program state described by eta can be preserved through the command C. And this is fine as long as these side conditions hold. All right, and there are other proof rules that you can see in the paper. But now let's go through an example of how we use PSL. So the one-time pad encryption scheme is what everyone learns in Crypto 101. So it goes something like this. To generate a key k, we're going to first uniformly sample from the n-bit strings. Then to encrypt the message m, we're going to take the XOR of the message and the key. And since XOR is its own inverse, to recover the message m, you take the XOR of the ciphertext and the key. Okay? So now let's prove perfect secrecy of one-time pad by an independence argument. So in the code shown here, in line 2, we have the key generation step. And in line 4, we have the encryption step. And so recall that the goal is to show that the distribution on ciphertext is independent of any arbitrary distribution on messages. And so we take as our precondition the following formula, which says that m has some arbitrary distribution. And then we take as our postcondition this formula, which says that the distribution on ciphertext is independent of the distribution on messages. All right. Now to go through the key generation step in line 2, we can apply the random sampling rule, which lets us adjoin the formula stating that k is uniformly distributed. All right. And then to go through the encryption step in line 4, we can apply the random assignment rule. And so this will let us conjoin the formula saying that the ciphertext is probabilistically equivalent to the message x or the key. All right. And so now to go from the formula in line 5 to the formula in line 7, we can apply a well-known axiom known as optimistic sampling. All right. So what does this say? It says that if we take some message m and we XOR it with a uniformly distributed and independent key k, then the resultant ciphertext c is uniformly distributed, and it's independent of the message M. Okay, so now if we plug this back into our proof, from the formula in line 5, we get the formula in line 6, which says that C is uniform and is independent of N. Now to get to our final desired postcondition, we can apply weakening, and then we are done. Okay, so that was the perfect secrecy of one-time pad. All right, now let's look at a fancier example known as ORAM. So if you were in the session yesterday afternoon, there was a very interesting talk on a language and type system for oblivious computation, and they verify various ORAM schemes. So this is our different approach. And so here, the model of computation we consider is a random access machine that runs programs in the following form. So program P is going to be a sequence of instructions I, and an instruction can either read from some register X, or it can write the value V to some register X. And so suppose Alice has such a program, and she wants to run it on her random access machine located in the cloud. Well, she might not trust her cloud provider, and so what she's going to do is she's going to encrypt the data that the program operates over. All right, and this might convince Alice that she's secure, but the question is she really secure? And the answer is she might not be as secure as she thinks she is. And this is because an adversary-controlled machine can observe the sequence of memory accesses. So it can see the accesses to registers x1 through xk for a program of length k. And we're going to call this leakage L. And so what ORAM gives you is a compiler that takes insecure programs P and produces an oblivious version of the program, such that when you run it, only the length of the computation is leaked. And then so what we want is this strong obliviousness property. So this PSL formula says that all of the elements of the leakage are uniform and independent. This implies probabilistic interference, and so no information apart from the length of the computation is leaked. All right, so there are many more examples in the paper that I don't have time to go through. And so just to summarize, our contributions were a probabilistic separation logic, and we apply this to various schemes in cryptography. There are many lines of future work, so we'd like to look more into expressivity, automation, and implementation. And on the application side, we'd like to look at the security for more advanced cryptographic instructions. All right, so that's the end of my talk. I thank you all for listening, and I'm happy to take any questions.
Hands of who wants to ask questions, so I optimize the mic. Okay.
In your definition, the star means it's a product of two distributions. What didn't become clear to me is along which variables do we split that? Because the problem is if I can split anywhere, I could have a formula that involves x on the left side, but I split my memory so that x is not even a defined variable. So it seems that where you split depends on the free variables in your formulas or something?
Yeah.
Or do you have to fix it?
Let's see. Let me go back to the example I had. What was that? Sorry, just a moment. All right, so like in this example, when we want to split mu, we have to find two disjoint sets of variables. So here, the example is x and y. And then by this Kripke monadicity property, if we have that this assertion holds over the product of mu1 and mu2 here, then it also applies to this other larger parent distribution.
Yeah, I understand in a concrete example, but formally I could split it in a way that x is for, I could put x and y both on the same side, and then the left formula in your product, it doesn't have a well-defined truth value. So, I mean, would it be a valid split or not? And what if I put a negation sign in front of the UB of x and so on? So
yeah,
that's,
I think in that case it would not be a valid split.
Yeah. Okay, I'll ask you later why.
Yeah.
Yeah, let's take this one offline. While I walk to the next person, I'll ask something from Slido. Is the PSL logic complete? And if not, why?
Good question. So it's not complete. So there are a few sources of incompleteness. One that I didn't talk about was, so I didn't go over the rule for randomized conditional, which is this Archon rule right here. And so here we require that the guard must be independent of the rest of the program state. And of course, this is one source of incompleteness. So looking at other rules would be interesting. Another source of incompleteness would be the interplay between uniformity, independence, and even the XOR operator. So it's not totally clear how to give a complete axiomatization for even just with the XOR operator.
Hi. So there's a lot of interesting, or at least non-trivial things around conditional independence. So have you thought about extending this to include conditioning and conditional independence?
Yeah, so that would extend the reach of our logic by a lot, but in this work so far, no, we haven't considered it, but it would be interesting future work.
Okay. Did you consider implementation in EasyCrypt or Iris? Asks Bas Peters.
Okay. Yeah, that would be very cool. So far, we don't have an implementation, but maybe be on the lookout soon, hopefully.
Thanks very much for your talk. So one of the nice things about heap separation logic is that it extends to concurrency really naturally. Does probabilistic separation logic also extend to concurrency?
It's not totally obvious how we would extend it to concurrency at the moment. Yeah, that's tough to say. I don't have a good answer at the moment.
Oh, okay. So I think we're done with questions, so we can thank Kevin again.